I have recently acquired a new detector for my collection, and this time it's a civil defense type, and it's a CDV-717, and it's incredibly similar to the popular and classic 715, which utilizes a fixed ionization chamber to the unit, while this one has a detachable one to measure radiation levels outside of a fallout shelter, for example, as these units were made during the Cold War in the 60s, and there was a lot of fear that it would become into a nuclear war. So these were made to reduce exposure for people in fallout shelters in case of nuclear fallout, and it's quite bulky but definitely durable. And this little department here in the case is the chamber itself. It's right in the front, and the entire case here can be detached by switching these little hinges right here, while these hinges will open the unit itself, where you can put in a new battery and also clean the circuitry. To begin with, I'll go over the front of the unit, which is right here. It consists of the gauge, a knob to operate the unit, and another knob to zero it. On the gauge, you can see that it measures in full or per hour. So it's definitely not really for your everyday sources, only for strong ones and, well, nuclear fallout. The little knob right here, selector switch, has a bunch of different modes. It has a circuit check, which you'll switch to before operating it to check if everything is working like it's supposed to, an off setting to turn it off, a zero setting to zero the scale as it likes to drift a bit when it hasn't been used in a while, a times 100 to measure up to 500 hour per hour, times 10 to 50 hour per hour, times 1 to 5 hour per hour, and 0.1 for 0.5 hour per hour. To begin operating it, we'll switch to circuit check to check if the needle lands within the circuit check box. So we'll turn it right there. You can see it seems to be working. Then we'll switch to the zero setting. Check the needle. We want it to be right at 0. And as you can see, it's a bit underneath. So we need to turn this 0 knob right here a little bit carefully. I'll move it a bit closer to slowly turn the needle into the right place on the 0 spot. It seems quite close, like that. Then to begin measurement, the measurements will turn it on times 100, times 10, times 1, and 0.1. And on the 0.1 setting, the needle will drift a bit back and forth. And this is due to dirt and grease on the circuitry inside of the unit. And that can be cleaned with the chemically pure isopropanol. And that should reduce the drift a bit. As you can see on my unit, it's not exactly on the 0 mark. It's slowly moving up and down. But it's not too much of the end of the world if you know why it's drifting. Could be quite scary if you have no idea why it's moving a bit. But that's give a bit of an overview of the more special part regarding this detector, which is the detachable ionization chamber. So we'll press down these hinges. This one. We can now remove the ionization chamber like that. You can see here that it has a little bit of a connector here. It goes right here on the chamber itself. And here it is, the inside. It consists of the chamber and the power cord here. And this is about 7.6 meters long. And it's pretty useful if you want to measure very high amounts of radiation but not stay inside of that area. I can remove it right here and see the two connector switches, where this one goes on the chamber and it has to be screwed on, while this one goes in the unit itself and has to be pressed in. And here's the chamber itself. It's this box which will measure the radiation. Right here, it's a little bit of an, I believe, aluminium can stuck inside of this aluminium casing. And then the other hinges inside of the detector will show us the circuitry. So we'll unhook these two to also show you the inside of this detector. See, it plops right out. Here's the inside with a bit of a manual over the circuitry and the connector switch, or well, connector for the unit itself. It's also aluminium casing. And here's the unit. Here's the circuitry. These switches right here is for the calibration. It's where you calibrate the unit, often to cesium-137, which is the main potent gamma source during a nuclear fallout. Here is where the battery goes. It's a little bit of a plastic box to contain it in case of it corroding. You just unhook this little aluminium piece of metal. Here's the battery. It's a diesel type, 1.5 volts. It goes right in here, plus at the bottom. And then you close it up, boop, and that's it. It's not really expensive to use as it utilizes so few batteries, just one. And as you can see on my circuit board, it seems quite dirty. I'm unsure if this is from the manufacturing or from it just being very, very old. But I'm guessing this is the cause for the needle drifting, the times 0.1 scale. But anyways, that's mostly it that I will demonstrate regarding the inside. So now let's actually demonstrate the unit in use with three main types of sources: a strontium-90 source, a radium-226 source for gamma, and an X-ray source. So let's begin with a strontium-90 source. So right here I got a pretty powerful piece of strontium-90. It has an activity of about 244 microcuries. It's a DP2 source, and we'll demonstrate it being measured by the unit itself. I have the power cord out here to kind of keep the unit steady. But let's turn it on, put it on the 0 scale, make sure that the unit is zeroed so you don't get any false readings. Normally you'd let the unit warm up for about 2 minutes, but I've already used it quite a bit, so it doesn't seem to require it to get any small readings. Seems about right. Let's turn it on the 0.1 scale. 0.1. You can see the needle move back and forth. As said, that's due to the grease in the detector. Let's put the source in front of the ionization chamber and see if we get any significant movement. As you can see, there's pretty much absolutely nothing. No difference whatsoever. And why is this? Well, as we know, the unit is constructed of aluminium in the casing here. And that's quite enough to stop a lot of the betas being shut out from this strontium-90 source. And that's quite important to keep in mind, as it will be very insensitive to beta particles. But there is one solution to this, because we can measure if we remove the casing itself. So I'll open it up, I'll turn it off of course, open it up again, and as you may see on the ionization chamber, there's 4 screws. This can be unscrewed to remove the ionization chamber, mainly in case it's broken, but in my case it will be to measure the betas. So the ionization chamber has been removed, as you can see right here. Here it is. I would not recommend this, as you're exposing, removing the case, the protective case from the chamber, which makes it way easier to damage. But this is just for my demonstration. So I'll put it, hook it up to the unit, just like so. Zero it a bit. Move it to the 0.1 scale. Let's focus on the needle. You can see it's drifting a bit. Let's see, put the source right on the chamber. And as you can see, it's moving. If I remove the source, down it goes. Back. It goes up again. Which demonstrate that the unit does indeed work. Sometimes the chamber can still be broken, even though it passes the circuit check. So it can be hard to know if the unit is working or not. But this one does. I have access to these sources, which is quite nice. But let's testing against a gamma source instead. Just to show that this is indeed a strontium 90 source, that I'm not faking it or anything. There's a radius scan. It's hooked up to a berry pack. Let's put it right in front, as you can see, and it's even zero. It saturates due to the immense strength of this source. I can hold it right here and it maxes. So it's a fairly spicy source, just to prove that it is indeed very radioactive. But let's move on to the gamma source. Here is my gamma source, Radium 226, about 1.6 millicuries of total activity. And to show you again that it is indeed quite radioactive, you can hold it right here. You can put the radius scan in front and it clearly maxes from fairly decent distance, might even zero close enough. Maybe not, I don't want to contaminate it. But as you can see, it's some pretty spicy stuff. 2 millisieverts of gamma only from the top. So here's the CDV-717. I got the case on to measure pretty much gamma only. It's drifting a bit, like usual, sadly. But here's the gamma source of radium. So I'll put it in front of the chamber, see if you can see any difference than usual. See if I get it right on top. Yeah, you can see it move a bit. It stays there, over 0.1 hour. It falls back down almost. That's it. But let's try it with the X-ray machine as a final test. So I have the unit now placed in front of my X-ray machine. It's right in front of the window, right here. A piece of styrofoam to keep it in place. So we'll begin by turning it on ×1, and I have the aluminium case installed still, just to let you know. But I'll turn it on 0. Make sure it's correctly on the 0. Seems like it. Turn it on 0.1. There's some drift. And I'll now turn on the X-ray setup, the X-ray machine, and it should max this mode and the 1×1 mode, mainly as a demonstration of the unit operating. So I'll move out of the room and turn it on. So I'm going to now turn on the X-ray setup and let's see the scale maps. 1, 2, 3. And off it goes. Of scale on the 0.1 R per hour. So let's turn it on ×1. Like so. And let's do the same test on the ×1. So up to 5 R per hour. 3, 2, 1. And it almost goes off scale. It would probably max normally, but the problem with these units when it comes to X-rays like this is it said that it has a pretty thick aluminium case. And that will absorb a lot of the X-rays, sadly. But it's mainly as a way to show that the unit still operates, and that's of course tested with the cable and the X-ray machine. As there's a little bit of a difference on how it measures radiation, like with the cable. So I'll set that up. And here is also how you connect it, just to demonstrate. So remove this cable, or remove a fairly long bit. Take this plug, if the camera would like to focus, which can be turned. So screw it on the ionization chamber. It's quite a messy demonstration, but it will have to do. Let's see if I can turn on the light. Got here, just screw it on, just like so, until it stops. See, and you just plug it right on this plug right here, and it's stuck. So then you just place the ionization chamber in front of the machine, in my case. So I have now placed the ionization chamber in front of the beam right here. You can see the cable going to the meter itself, and I know it's very messy. You'll have to excuse me for that, but let's turn on the unit first. Seems good. Turn it on the 0.1 mode. Cable, so it will be much slower at registering the amount of radiation. I believe it's on the 0.1, it's up to 4 minutes to get a decently accurate measurement. But it gets lower and lower every time you increase the scale. But let's turn on the X-ray setup. You can slowly see the needle move, very, very slowly. And said that's due to the cable being used instead of, well, the chamber directly installed in the unit. We can turn it on ×1. To zero it, I usually just turn it on ×100, ×1. Turn the machine on once more. And slowly see it climb on the ×1 mode. Very, very slowly. So it registered 1 R, and even though it was so high, way higher than the 0.1 mode, it still climbed so slowly. And interesting. And to try one more thing, and just to show you that there's no high voltage interfering with the readings, I put the camera in the beam to demonstrate the intense amount of X-rays, that it's actually measuring X-rays and not high voltage interference. So I'll put the camera right in front of the beam to demonstrate the intense amount of radiation it's actually measuring, so you know it's not false readings. So let's turn on the X-rays. 1, 2, 3. As you can see, there's a hell of a lot of flashes. So it's indeed measuring radiation, and not any high voltage interference. But that's it. I'm sorry for the mess, and I hope it was quite interesting.